All right. Get some tunes going over here. Before we start, just gonna noodle a bit on the melodica. Let's see, what key are we in here? Down a little bit. Turn my mic up a little bit. That looks pretty good. All right. Today we are going to be working on this. I guess I should put it this way. No, I should put it this way. There we go. This is the KBD67 As you can see on the back, KBD67 Mark II RGB V2. Wow, it's Mark II and version 2. That's amazing. So I'm not going to be doing a build today, really. Well, I guess I'm doing the very beginning process, but I'm going to be doing design. I'm going to be taking measurements and starting the design for a case for this keyboard. So I'm going to be using these. Engineer's best friend. A nice pair of Mitutoyo digital calipers. I'm going to be taking measurements from this here PCB, and then we are going to be modeling everything in Fusion 360. So yeah, I've got Fusion 360 up, hopefully. Boom, there it is. Cool, we got a blank new design, but first we gotta take some measurements. So first of all, I'm gonna take a measurement of the inner diameter of the post holes that actually mount everything. This one is a kind of a sandwich mount. But yeah, so I'm gonna first get that inner diameter. Just take a little dimension. 2.36 millimeters. We'll see how consistent that is. I'll do a few of them. 2.42. Here, let's do a notepad. Actually, you know what? I'm gonna actually make a Google document. And I'm going to make a new Google spreadsheet. And keyboard PCB dimensions. And I'm going to call this tab KBD67 Mark II RGB V2. Okay. Dimension value 1. And we're going to have an average. Boom. Post hole ID, inner diameter. So we're going to take some averages here. 2.37. 2.45. And then we'll do a third dimension on this one over here. 2.39. The first one seems like a big outlier, so I'm going to measure it again and just make sure it wasn't just kind of off center. Was it this one I did first? Oh, it's showing 2.44. If you're taking measurements and doing an average and one of them just seems way different than the other ones, it's a good idea to just go remeasure that one and make sure you didn't mess up your technique. Because, using calipers requires some technique. So yeah, there we go. 2.43 is going to be our average for our inner diameter of the post hole. Yeah, so let's bring up Fusion, and this is the parameters. You can get to them by going to modify, change parameters, and I have it set to Control P. That's not there is no stock default key combination to get to it, but you can set up your own custom ones, so I set up Control P for parameters. I'm going to set up a new parameter, and I generally make anything that's like a measured value that will never change in all caps. I'm going to move my keyboard a little closer to me. So we're going to say this is post hole ID for inner diameter, and that's equal to 2.43. I do everything in millimeters generally. I'm going to go get the plate for this PCB so that we can check against that. So this is the brass plate for this PCB, and this is where the space bar would go. This is where the switches, and this is where the stabilizers go. We can tell, holding it up, putting it over there, that these holes match up perfectly with these posts, as you would expect. So this is the correct orientation. The USB-C hole is going to be on the left and the back. These are hot swappable switch mounts. I don't have any switches near me, I don't think. I just put all my switches away. But anyway, what we want to be sure of is how the whole board gets constructed. So, since these are countersunk from the top, and this is sandwich mount, I'm going to go ahead and assume that the hardware goes down through the holes in the KBD67 PCB. I'm going to check something really quick. So just gonna check a reference real quick. Andy Wen has a good video about KBD67 builds, so I'm gonna check that just to double check exactly how the construction works. So I actually am not going to buy the case or anything else for this keyboard because I'm gonna make everything myself. That's one of the nice things about 3D printing and engineering and stuff. CAD, I mean, you don't need to be an engineer to do this kind of design. It's pretty simple, honestly. But I can pay for just the circuit board and the plate and then just design a case based around that. Obviously, I need switches and keycaps. But that's it. So I don't need to buy the case, which usually saves you around $100, maybe more, sometimes a lot more. So if you want like a really nice key cult or something, or whatever fancy keyboard brand you like, if you can find just the PCB by itself and you get some calipers, some CAD software, Fusion 360, which I use, is free, with either an education or a startup license. So if you're a student, yeah, it's a great way to get an affordable mechanical keyboard. So it looks like it comes with some different types of hardware. And, okay, yeah, sandwich construction. So the case is in two pieces, the bottom part and the top part, and this is sandwiched between them. I just want to see, okay, so there's hardware that comes with this plate, and it's little screws. They look like M3s, which are usually used for cases, which I have some of those, so we can use those for dimensions if we need. Plus, you can just look them up. But it does look like those grew into some standoffs, and the standoffs, I'm guessing, are threaded, and then I'm guessing you just screw a screw into the other side of the standoffs. I'm gonna have to go to KBD Fans and buy some of that hardware, or I can just try to find the dimensions and just 3D print the standoffs, which would be very easy to print. On the resin printer, definitely have the good enough tolerances for a small part like that. So he's got the standoffs in there, and then he pops everything into the PCB. Yep. So that's it. So yep, that's how it works. There are little brass standoffs that go under here, and then you screw them in from the top, and then there's a threaded hole in the bottom of the standoff, and that butts up against the bottom of the hole here, and on the other side you would put a screw in from the bottom into the standoff. So cool, we know how that works. Our case isn't going to need any it's not going to need any posts printed into it like most 60% cases would, because the posts are going to be connected to the plate itself, and this PCB is going to be held up from above, which is kind of how sandwich construction usually works. Here's the reset button. We're going to want to know where that is so that we can reset it and do QMK flashing and stuff like that. Usually if there are LED underglow lighting, I'll measure where those are, but this is all these LEDs are facing up for backlighting for the keys. So if we want to add some underglow or side glow in the case, we're going to have to buy an LED strip and connect it to power somehow, which, let's check that out. Here's the USB-C port, looking for the power delivery system. There's a little capacitor here. These diodes are okay. Here's the main integrated circuit. Some resistors there. Yeah, I guess it all runs off of 5 volts because I don't see any kind of voltage regulation. We have guaranteed 5 volts from USB-C. There are some resistors and capacitors here just to take care of stuff around the chip. Yeah, there's not really any way to connect up any extra RGB. Wait. Ground, reset, VCC. Well, we can plug it in and measure that, but yeah, for now let's just get some of the main dimensions. Let's go back and I'll take some measurements here. I'm going to measure the thickness of the PCB itself, usually important. It's usually good to model the PCB itself in the design just so you can get an idea of where it's going to be. I usually model the plate and the circuit board in the case model. 1.64 is our first measurement. Okay. So PCB thickness. 1.64 was our first. Take another one from a different part. Make sure you're not scratching it. And 1.61. And also make sure you're not going over any components on either side or any other layers like a metal layer or something, because you want to get just the thickness. 1.62. Boom. I'm going to take our little average thing. So I've just got a Google spreadsheet open with 3 columns for different values. Each row represents one of the dimensions. So there's one row for the thickness. I took 3 different measurements and then I averaged them. So 1.62. I'm going to take just 2 decimal places. So here's our Fusion 360. We're going to add PCB thickness. Double check. I think that was 1.62. Boom. So there's our PCB thickness. All right. Zero that out. Let's get the height. That's probably the next most important thing. Now, these are only 6-inch calipers, which is pretty common. I kind of regret not getting the longer ones. They're a lot more expensive, but sometimes it's nice to be able to get really accurate measurements of something pretty long. Okay, let's see. We'll try to line it up and get parallel with the side to get an accurate measurement. 92.14. Okay. And generally, the bigger the measurement, the less important it is to need like an average. These are all pretty similar. It's not always true, but the case is going to have ample room around the sides, so the height of the case doesn't need to be the most accurate thing in the world. So I'm definitely not going to be able to measure the length of this thing with my calipers. So I'm going to go get a measuring tape. And I'll be right back. Hey everybody, sorry I had some mic issues. I'm back now. Let me just double check something. It's still recording, cool. Alright, so yeah, I just went and did some of the boring stuff. Got the thickness, the plate, width, the height of the plate. So since this is going to be a sandwich mount construction, the plate is going to be holding up the PCB, so we don't need to know any of the placements of these holes on the PCB or the plate, just these 6, 1, 2, 3, 4, 5, 6 on the top and bottom. Those are the ones that are actually going to screw into our plate, to our case. So I've gotten these 3 measurements, the X measurement, and then I'm going to get these ones, and then I'm just going to find, it seems like they're all the exact same distance from the edge, so like the Y measurement. And then with our plate, actually it almost seems like they're perfectly, the bottom edge of the hole is perfectly aligned with the edge of the plate. Let me get something straight. Not quite. Very close. Very close. But anyway, yeah, then we'll only need 1 measurement for the Y distance for all the holes. Yeah, so we're almost done with the boring stuff, and then we'll get into Fusion 360 a little more and start modeling some stuff. I'm going to model the plate first because it's the driving piece, then the PCB, but everything will be based off of the plate. Right. So, let's see, this hole to the left edge. $24.99. I'm guessing that's 25. Yeah. So we're gonna add another dimension, hole 4 to left, 25 on the nose, and hole 4. Can I get this measurement? $153.67. And last one, we're going to have to take from the right side. $20.26. Hole 6 to right. Boom. We've got all those. Now we just need the measurement this way. I'm going to get this whole tab because I'm going to want to model that in. And these little guys seem important. I'm guessing the case has little indents that these lock into just to kind of align everything. Same with maybe these guys on the right and left. But most importantly, yeah, we need this stuff. So for this one, I'm going to, actually it might be better to measure it this way, like that. No, this one will actually work a little better. .27. Sorry, 3.3. 3.4. 3.4. Plate tab height 3.4 millimeters, and plate tab width 5 point, looks like 5.4. We want it to be like right there. .45 millimeters. Okay. Now the height from the center of the hole is going to be a pretty difficult thing to measure. What we can do is we can get the height from hole to hole. I'm trying to find two holes that are right above each other, which these two are. And I'm going to measure it edge to edge and then subtract 1 diameter. .93. 102.93. So plate hole vertical edge to edge is 102.93. All right. And yeah, basically it's like they made it so that these holes would be pretty much the edge of the hole. It lines up right with the edge of the plate. It's up by a tiny, tiny amount. It's pretty much right on. So we can go by that for a little while. Let me see. It's a better way to measure this. We went from the center of this hole. Yeah, I think the best way actually would be to measure the hole edge to the plate tab to edge 1.2. Wait, 1.04. 1.05. .05 millimeters. Cool, then with the circumference the inner diameter, or sorry, that inner diameter, we can figure out how far the holes are away from the edge of the plate. Cool, so now let's get into some real 3D modeling. Normally I would start with the PCB design, but the PCB is actually not very consequential in this because it's sandwich construction. The only thing that's really important on the PCB is this USB-C placement and the reset button placement. Everything else doesn't really matter too much. So yeah, we're going to do this. I'm also going to scan this in the 2D scanner and import it as a what's called a canvas in Fusion 360. But yeah, let's pop on the Fusion 360, get Streamlabs out of the way. So we've got all of our measurements here that we took and the parameters. So these are all caps because these are all measured, so they're basically like global constants. I'm just gonna go back to Facebook real quick. Okay. So let's show our origins. I have mine set a little differently than the default. I put my XY plane at the bottom, so you look down from the top onto it because that's how 3D printers are set up. So I have it set so that when I export an STL file and open it in a slicing program like Cura, Chitubox, or Prusa Slicer or whatever, it will be oriented properly because the default Fusion 360 layout has the Z-axis, I think, facing towards you or whatever, which like where my X-axis is right now, and that makes it so you have to reorient things every time you want to print them. So I changed it like this so whenever I save STLs, it saves them in the right orientation. We are going to make a drawing on the XY plane. So create sketch. Look at it. And we are going to make a big old rectangle. And I like to make a construction line across it. And we'll do a point on it like that. Then I'm just going to take that and the origin and coinky-dink them. That way, everything is perfectly centered the whole time. And when you like insert canvases or decals or images or whatever, it always, when you stretch them, to fit perfectly, it always does it from the center. So it's just easier to have everything centered. Right, so we're going to use some of our dimensions. So we hit D for dimension, go to the bottom, and that one's going to be plate width. Boom. So we got to zoom out a bit, and then we'll do one over here. Plate height. And that's going to be our basic plate. I guess we should put the holes in here, but we can add those in a second. But that's going to be our basic plate. And just so we have something, I'm going to say that the top of the plate is the top of the design. So the XY plane is parallel to the top of the plate. That way everything under that, the standoff and the PCB will be further down. Otherwise you'll have like the plate be above the origin and then the PCB below the origin, and it's very confusing. So we'll extrude down only, and we're going to extrude thickness of plate thickness. We already have all these stuff defined, so all of these dimensions are easy. I'm going to change the appearance just so it's a little easier to see. Well, first let me save it. We'll save it in mechanical keyboards. New folder in there. And we're going to call this KBD67 case. And we're going to call this KBD67 case. There it is. We got the file started. So this is honestly one of the biggest steps. We got all the most important dimensions, and we've got the Fusion 360 file started. And yeah. So here's our plate. All right. Change the appearance. I usually just like to go into plastic and just use white ABS because it's a lot easier to see. How do I make that? Okay. It's a lot easier to see instead of shiny metal stuff. And I actually almost always work in perspective view, which is when the shapes look like real life. I don't like orthogonal view if I'm looking at something in 3D. I only use orthogonal when I'm doing sketches and only when I need to project something from a different sketch and be able to see where it is. Usually sketch actually slightly off axis in perspective so I can actually know and see exactly how it's changing the model. So there we go. That's our basic plate. Obviously it doesn't have any of the important stuff and it's just a big rectangle. I kind of want to measure these indents. I've got 1, 2, 3, 4, 5, 6, 7, 8 indents. These ones are on the corners. So yeah, let's do that real quick. Side indent width. I'm just going to measure the full width of the entire thing. Say that's 5.45. Okay, and the depth. Let's see if these are the same. .97 and 0.81. Let's measure the width of these inner ones. Four millimeters. And the depth, this isn't super important, but .53, that seems too short. 0.7. Okay, then we just need, these look like these are, I think I can assume these are in the same spots. The center of that one is about 103.62 to the edge. This one is, yeah, 103.62. Okay. Plate, indent to edge. Let's just double check that. We'll say 103.7. Okay, so now we'll go back to our plate sketch. Let's rename that. Always name everything. I'll call this plate master sketch. And we're going to edit it. And now we're going to add some of the indents. Trying to think of the best way to do this. In the sketch or out of the sketch? I think let's do everything in the sketch. Right, so we can just do something like this, and then trim. That's annoying. Right. Yeah, okay, we're gonna have to delete these for now. This is symmetrical. Mirrors sometimes do weird stuff in this program, so I'm not super hot on using mirrors for one of the base parts of the drawing. So let's just say, let's just do everything manually. We're going to cut out little rectangles on all the sides, trim them, trim that, and that one, and this one. Okay, let me make sure of something here. Okay, now I'm going to say that this edge and this edge, damn it, that edge, and this edge, and this edge, and this edge are all equal. Okay, and then the little ones, that one, and that one, and that one, and that one are equal. Great. And I'm going to dimension this edge as being indent, plate indent depth. That's right. And we're going to dimension this one as indent, plate side indent width. There we go. Now when we move this, that should move, and this should move, and those should stay the same. This needs a new constraint. This and that one should have a midpoint constraint. And just to double check, this one and this one should also have a midpoint constraint. So now that should move together, that moves together. And now we're going to dimension it more like this, from this edge to this edge is plate width. And from this edge to this edge, plate height. Boom. Everything's fully constrained. Now let's add the little indent tabs. We are going to put one of them here. We're going to do an arc like that. And we're going to dimension from see. No, that's not the dimension I want. Let's do this. We're going to make a construction line from here to here and make sure it's parallel to this. And the distance from here to here is going to be indent depth. Okay. And we do the same thing on the other side. Now, you could definitely do all this stuff with the mirror tool, because this is all theoretically symmetrical. But Fusion 360's mirror tool just does really weird stuff sometimes. If you're doing parametric design, it breaks all the time. Like, it'll just drop the mirror constraint, and then things won't be mirrored anymore, and they'll just start flying all over the place. I have no idea why. But if some change, like, overrides the mirror or, like, does something to it and pushes it a lot, it just breaks, and it stops being a mirror. I don't know why. Something that Autodesk will hopefully fix. So, depth. Plate indent depth. Just like on the top side. And we're going to have 2 arcs. And, oopsies. Why isn't... Okay, so the arc's going to go from here to there, and then it's going to be tangent to that. And then we just set dimension from this point to this point to be with alright, and then we do dimension from here to here, and that's plate indent to edge. Okay, then I'm just gonna copy all this, move it over here. Those ones and those ones and those ones all be coincident. What? Okay, let's try this one at a time. You and you, coincident. You and you, coincident. You and you, tangent. And then finally, dimension from here to here is indent to edge. Okay, and we'll do the same thing on the bottom. You to you, tangent, and you to you, plate indent width, and this to that. Okay, like that, tangent, and you to you, And then U to U. Boom. So that's done. Now we're going to do the holes, and at some point I'm going to do fillets. Trying to see where we really need them. I'm not sure it really matters too much. I don't think our case is going to wrap that tightly around. The only place that I see really obvious fillets is around there and around. Yeah. I'll save fillets for the last. We need to add the... Let's first finish this and see how everything looks. Turn sketches off. And we can see our little cutouts. I think those little guys. Right. Yeah, so what we need to do is edit this. Now it automatically, see, Fusion 360 thinks I want to keep the inside of this part because it was part of the extrusion before, but I don't really. So I'm just going to reselect the inside, just the inside. And alright, so now we've got our nice little indents, which we can use to design the case to have little things that jut out into those for alignment if we want to. Looking pretty good. I'm not going to model all the holes of like where all the switches go and stuff because I'm not going to be 3D printing this plate. Yeah. It's looking pretty good. Let's add what's the most important thing, which is these tabs that the actual plate gets held onto the case with. So let's go back into our sketch. So I'm basically just going to make the sketch as accurate to the plate as I can, only including the stuff that's important. So I'm going to make a little rectangle, attaches onto here, and I'm just going to do all of them about the same spots as they are in real life. Doesn't really matter about the size. We're going to constrain these in a second. And I actually want to make sure I don't have it snap to anything, so I don't want it to add any dimensions that I don't intend for it to. So a lot of the time when I'm drawing stuff, I'll like intentionally make it kind of a weird shape or like crooked or bigger than it needs to be, just so that I'm making sure it doesn't snap to match something else or make it parallel. I basically like to add all of my constraints manually. That way I can control all the constraints. Gonna take a quick puff. So we're going to set the width of all of these tabs to be the same and the height of all of them to be the same. But first I'm going to trim the plate. I'm wondering, actually, if I get this plate drawing very accurate, I can probably just use the offset tool to design the case, because it'll get us all of the tabs and make cutouts for these tabs. But yeah, I can use that. So I'm going to have something that this plate sits on top of and goes into it a certain amount, like underneath it. But we only want it to be supported by these points. That's kind of half the point. of a sandwich mount design like that, so the keyboard can flex a little bit in the middle. Yeah, the distance between these is about the same as the distance between them vertically. So yeah, the plate will only be held by these points. So the case isn't going to go under this part at all. It's only I'm gonna have one part under these to hold them up and for the screws to go down into. And everything else is just gonna go around the outside. Okay. Yeah, let's get this done. We're gonna trim this guy. Trim this guy. And this one. Go around here, trimming. You know, oopsies, don't want to trim that one. I might not actually want to trim these parts. In fact, I'm going to probably could have gotten away with not trimming anything last time. No, that's pointless. Yeah, but let's not trim the tabs, because it's gonna split up the main lines, and we're just gonna have to add a ton of constraints to keep everything held together. So the tabs are gonna stay separated. We'll just select them as another profile when we extrude it. That's fine. But we are going to say that this and this, and well, we don't really need that. This one and 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 this one are all equal. Boom. And the width, this one and this one, number 3, number 4, number 5, number 6 are all equal. Then we're just going to dimension the top left one. That one's going to be, actually, you know, it's probably a better idea. We'll dimension from here to, oh, that broke up this line anyway. These are all separate lines, huh? What happens if I try to drag this line? So maybe I can trim it. It says constraints and or, let me see if it'll tell me which constraints. That's it. But were they? Were they really removed? Because nothing turned blue. Everything is still white, which means it's constrained. That's still equal. That's still equal. Yeah, okay. Let's go ahead and trim it then. This is a little different from how I often sketch I wanted to make one sketch that's basically just exactly this plate. But usually I will kind of make a sketch that's just a simple rectangle, and then I'll extrude that, and then I'll add stuff to it with later steps. Why is there a line showing there still? I do not know. Did I not trim this one? And we'll trim these guys too. This one should not be blue. Why are these blue? I can't change these. These should be fully defined. I don't know. Was it blue before I trimmed it? Yeah, these ones are blue for some reason. I don't know. Figure it out later. I think it always says constraints or dimensions were removed whenever you trim something. Because that one's still white, so it's still showing as fully constrained even though I trimmed it. I don't know why this one isn't. Anyway. Save. So, now all we need to do is dimension this and say that's equal to tab, plate tab height. And this one, tab width. Cool. And we'll make a circle in here. That's going to be the hole in the tab. I want to see what happens when we do a fillet. You can do fillets in sketches too now, which is cool. If I add a fillet, will it screw up the constraints? Yeah. So I want those fillets in there, so I'm going to do these dimensions differently. I'm going to do this one from this edge to this edge. And this one from this to this. Now let's see, we should be able to add a fillet without breaking those. Okay, cool. I'm not going to do the fillets till later, but I wanted to make sure they wouldn't break our dimensions. So that's looking good. And now we'll add a circle. And we'll dimension that. Actually, let's add little circles all over so we can make them all equal diameter. Don't want any auto constraints. So I'm just making the holes whatever size, trying to avoid the green lines. I should probably just turn off snap to constraint, but sometimes I like to use it, so I don't know. Okay. Now we're gonna select all of our circles, and yes, you probably know what we're gonna do. We're going to select all of them at once and make them all equal to each other with an equal constraint, and then we're going to set the diameter of them only on the top left one. It keeps our drawing from having tons of dimensions and it saves us some time. So we'll dimension this and we'll say plate hole inner diameter. Boom. Now they're all the right size. And they should all be in the center of the plate horizontally. So It's the easiest way to do that. I guess we can have a construction line and have it go to the midpoint. Yeah, I guess we'll just do this. And I actually do want to use that. And we'll make that construction line. And then this and that are going to have a midpoint constraint. Oh, but no, I don't actually want it to be a midpoint constraint because it's actually not going to be in the midpoint. I'm just going to say okay, I'm going to add these little construction lines on all of them. Now, tonight I'm only looking to get this to the point where I can do a test print of these holes and see if they're in the right spot. Maybe do an outline of the plate. So actually getting pretty close to being done here. And then next week I'll do a stream and continue this, and we'll get into doing more of the actual case design itself. But basically, to make a case for something, you just have to model that something that it's a case for first. So I'm going to select this line and then all of these lines. Like if I wanted to make a case for my calipers, I would have to basically just model the calipers completely, and then I could build the case from there. So this is a necessary part of the process. I'm going to say those are all equal. Boom! Now all of our construction lines are nice and the exact same height. Save. So this one and this one should be coincident, but they shouldn't necessarily be midpoint. In fact, I don't think it's going to be. From looking at it, it looks like it's pretty much going to be like right there. I'm actually going to try to use that as a constraint at first because it looks perfect. I think that's how they designed it. Yeah. Now we need to get the positions of this thing. So basically this whole placement is going to be driving where these tabs go. I'm actually just going to make a construction line from here to here just to make things easy. Probably could have just done that earlier instead of using the equals constraint. What is going on? Cool, so we got this construction line. And now we can say that construction line and this are tangent. Alright, it's starting to look a lot more like the real thing. I'm going to add those fillets in once we're done with all the holes, but finish up this first one from that to this edge. That's hole one. Wait, what? Hole one. Oh, I think I named that one wrong. Hole, yeah. Hole one to left. Okay. Now that one's going to be hole one to left. Boom. That's its final dimension, hopefully. And then we're gonna do this one. So this one and this one are gonna be coincident. Add a construction line from here to here. Why does it Fusion? It's like slowing down whenever I do that. We're gonna say this circle and this construction line are tangent. And then we say dimension the center of this hole to this line. Hole 2. Boom, so easy. It's nice when you have all the dimensions already. Then we go to hole 3. Your coincident. Your construction line. I don't know why my computer's slowing down when I do that. Okay. Tangent, and then we do dimension from this hole to this edge. And it's hole 3 to right. Boom. Save. Alright. You are coincident. And we have a construction line from there to there. I'm going to take a little puff. Okay, you and you, tangent, and then dimension from you to you. That's hole 4 to left. Boom. Go to this one, you and you. So whenever you're modeling stuff, it's kind of unavoidable to have to. Why? Did this one not get trimmed for some reason? What is this line? Oh, ha. Okay, it's one of the dimension lines. Whatever. Right. Unavoidable to repeat yourself a bunch. I mean, you want to try to minimize it as much as you can, but don't use the mirror tool to do that, at least in Fusion 360. In SolidWorks, it's a bit more reliable in my experience, but I don't know, it's just given me so many headaches. I think my top-down camera just... No, it's working. Actually, you can stop recording that. Cool. Yeah, I mean, sometimes you're going to have to do the same kind of thing a few times. And it's just basically how much you can stand. You can use pattern tools. But any fancy higher level tool like pattern tool, mirror tool, it's going to be less reliable than just manually modeling it out with a sketch, usually. Sometimes, I mean, like if you're going to do a honeycomb and cut like 1,000 little hexagons out of something, use a pattern tool, obviously. But if it's really dimensionally important, I wouldn't rely on a pattern tool or a mirror tool necessarily. I mean, you can try it, test it out. If it gives you headaches, go back. Fusion 360 is nice because it's got a timeline. You can just go back to wherever it is in the timeline and do it a different way. So anyway, this one and this one are going to be tangent. And then this one to this one, get a dimension, and that's hole 5 to left. And then last one, here we are, home stretch. That goes there. They're coincident. And then this one, gonna make a construction line. Oh, I think my keyboard doesn't like being pushed that far against the thing. To there. All right. This one and this one going to be tangent, and then this one to the right side is going to be hole 6 to right. And that's it. That's all the important dimensions. I'm gonna have to redo this extrusion, clear all those out, and then we're gonna select this one. And actually that's it. Just one profile. Boom. I'm gonna have to go in and do the fillets. I might do the fillets as solid body fillets in this. If you do a fillet, like here, I can click fillet and then click this edge and say 1 millimeter or whatever. That'll add a nice rounded fillet like that. Fillets usually aren't super dimensionally important. So I try not to do them in the sketch. It really confuses things in the sketch because usually your lines like this line and that line represent important dimensions, and like they do in our sketch here. And once you do fillets, those lines get shortened because it's not a straight line anymore. You could make it a construction line that's a straight line and then have the fillets be the solid line, but it's kind of ugly. So yeah, I think I'm going to leave this sketch like this and have the extrusion to have these sharp edges everywhere. Then I'm going to do a fillet after the fact. In fact, let's do that now. Let's call this plate extrude. Save, hit F for fillet, and we're going to select all these edges. I could kind of try to do all the fillets in one fillet feature because you can add multiple like groups of fillets in here, but I rather actually like having each fillet that's going to have a different, or possibly have a different radius, be a different feature on the timeline. That way I can see on the timeline by just quickly glancing like, okay, and they all have names, so there's that metadata associated with the fillet. We'll just call this 1 for now. That looks pretty good. Parameters, let's start adding our fillets. These aren't going to be measured because measuring the radius of a small fillet is pretty much impossible. Yeah, it's pretty much impossible. What I actually do for fillets is I'll literally hold up the actual thing in front of the screen and like close one eye and do this number and just look at it and see if the fillets match up, and then I'll print out a test piece and see if they match up. Usually for the test pieces, I make them way thinner than the actual thing's going to be, so it prints really fast. A lot of the time, it'll be like just one layer, like literally just one layer on the print bed. I'll drop the thing onto it, see if it fits, if it, and then peel it off the print bed, throw it in my filament recycle bin, and then do it again. It's all about the iterative process. You're never going to get it right the first time. Which is good, because that would be way too much pressure. So we'll just call this plate tab fillet. So I do camel case, not real camel case because the first letter is capitalized, but whatever, for anything that's not a measured dimension. So yeah, plate tab fillet. In fact, it looks like the could be a different fillet. Screw it. I'm just going to call it all the same thing. Plate tab fillet. We'll say 1 millimeter for now. That way I can change it later. So we're going to edit the feature, and instead of saying 1 millimeter here, we'll say plate tab fillet. And now if I go into parameters and I have this up here, let me go and make that a favorite. Favorites are nice. So you can ignore all the other messy things. So we can say that's 1.5 millimeters, and boom, all of the fillets just changed. And actually, I'm gonna edit that feature again and just add, I know I just said that I don't like doing this, but I'm gonna say these are all the same size. So I'm okay with these all being in the same fillet feature on the timeline. These inside fillets, I think, are the same radius, and if they're not exactly the same, they look very similar, and yeah, not super important for the case design. Okay, and these ones are also going to be plate tab fillet. Plate tab. Why? Okay. Turn sketches off for a second. Yeah, that's starting to look like the real thing. So go to plate, and here it is. Here's me doing the thing. So I'll like just hold it up, and it looks like it's actually a little smaller. So we're going to our thing up here, and while I'm holding this up, let's try 1 millimeter. That's too much. A difference 1.2. That's looking pretty darn close. Yeah. That's it. 1.2 millimeters. Good enough for government work. So boom, our plate is almost done. We have to do one. Actually, you know what I'm gonna do? That's a fillet, but that one's just a radius like these ones. I'm gonna edit our sketch one more time. All these ones, I'm gonna add, how should I do this? Add a 3-point arc. No, it should be like an arc, the same arc as these ones. That's what it looks like, but then it goes to a straight edge. Okay. That looks good, and just so we don't have a bunch of profiles we don't want, is that really pretty much, yeah, I think that's pretty much how that thing works. That's probably the best way to do that. Honestly, I should have not trimmed these parts off, because now I have to add this construction line here. I could have avoided that, but hey. It's fine. this is a little vestigial part of the arc, but if you trim arcs, it breaks any constraints you had to that arc. So I would strongly recommend against trimming arcs or circles or ellipses. Just deal with the vestigial thing. You need a complete arc for Fusion 360 to treat it as an arc and allow you to do like tangent constraints or like, you know, have it work like arcs do. So I'm just gonna do, this is 5.45. You know what I'm actually gonna do? I actually don't need this thing. And in fact, what I'm gonna do is add a construction line from here out to here, and that should be, yep, it's horizontal. And then we're gonna dimension that and say it's equal to the tab width plate tab width. No. .45? I thought it was 4 millimeters. Oh, indent. Yeah, okay. Wait a second. This is... Okay, yeah. Those are exactly the same? Huh. That's funny. Plate tab width 5.45. Plate side indent 5. Well, yeah. They're exactly the same. It's probably by design. So this one is going to be, these are called indents. I had a plate indent width. And I'm going to go ahead and do the same thing on all the other ones. You kind of want to do everything like assembly line style. I know that that is kind of depressing sounding, but yeah, if you're doing some action and you know you're gonna probably need to do it more than once, just do them all right then, because then you can do stuff like this where I make all these 4 construction lines and connect all of them together, select them all, and say they're equal. And since I've already defined that one as 4 millimeters, then whoop, all of these ones will be 4 millimeters. And you can, if you want to just check how wide something is just dimension it and then escape out of it, or you can do a over-constrained dimension where it's just redundant, but you just have it there to kind of show you. Yeah. So now we're going to just take this arc and make that coincident with that. Boom. That's exactly what this looks like on the plate. It looks like they took the same radius they're using for these inner ones and then just cut it off. They probably, when they milled this out, when they had the drill bit or the milling bit or whatever that they used to make these ones, they did the ones on the side too. And then when they had the milling one that went around the edge, it just filleted off this and made a straight line off of the other side of it. That's my guess. It's always a good idea to kind of think about the machining process, especially for the thing you're actually designing. So we're going to make another 3-point arc from there to there to there. And we don't want that to be construction. We want that to be a real thing. And we want this one to be construction. That way, yeah. Perfect. 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 Oops. Got a little bit of feedback loop there. Right. and make that construction. Then we do an arc knot construction from here to here, and then tangent there. All right. And from you to you and tangent there. Okay. Make that construction. Alrighty. I think that'll do it. Oh, look at that. That looks great. Here, I'll show you. You can see here. If I bring this up, that's, I mean, it's kind of hard to see. But yeah, that's the thing we modeled, and I'm pretty sure I modeled it the way they designed it. Basically just reverse engineering this thing right now. Alright, back to Fusion. And we're going to do one more a fillet around the corners. Before I do that, just proactively make a plate plate corner fillet, and we'll start with 1mm. Okay, boom, fillet, edge, 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 and edge. These ones don't have a fillet. It kind of looks like they do a little bit, but I think that's just the radius of the milling head that they were using was a little bigger, and it kind of just knocked off the corner. So, plate, corner, fillet. Boom. Oh, look at that nice roundness. Now we do the eyeball test. Bring up our parameters, and then we bring this thing to a place where I can see the corner. I'm gonna go down and favorite this one too, so I can access it easily. And looking at that, that looks fine. Alright, save that. Now we've got our plate and all of the driving dimensions. So, I'm going to make something that I can use as an STL. I mean, I could just save this as an STL, 3D print this whole thing, and then just put it on top of this plate and see if everything matches up. But that would be a huge waste of plastic. Printing big flat things uses a ton of plastic because the bottom and top layers have to go all the way across the whole plate and like color the whole thing in. It's a good idea to imagine like when you're slicing something, like if you're coloring it in with a crayon or something, if you color in the whole thing with a crayon, you're going to use up a ton of crayon. On the inner layers, you could just use infill, which is just a few kind of zigzaggy crosshatch lines, which you wouldn't use very much crayon at all, you know, if you were drawing it. But the top and bottom layers are always colored in all the way. So big, wide, flat things that are wide and flat on the bottom and top use a ton of filament and take a ton of time to print. So you generally want to avoid that if you can, especially when you're doing test stuff. So all we really care about is these indents and these holes, mostly only the holes. So what I'm gonna do, turn sketches back on, plate extrude. I'm gonna rename these just as you go. Keep renaming stuff, make sure everything's up to date. This is going to be plate tab fillet plate corner fillet. Okay, and yeah, we're looking good so far. I'm going to go to bodies, and I'm gonna rewind the timeline to right when this body came into being, and then plate. Yes, I probably should have made an extra component in this and made this whole plate inside a component. Let me see what happens if I rewind the timeline all the way. And go to this body and then do can't you do create components from bodies? Alright, now it doesn't like. Yeah. Not gonna work. Well, I'll figure that stuff out later. Fusion 360 is this an annoying thing about it. With the timeline, there's no way to move a timeline with something. Like, I can't move this plate to a new component in this design and have the timeline go with it, which is pretty annoying. I think they kind of accidentally coded themselves into a corner, and with that one, they would have had to design it from the ground up, having that functionality, so it's probably going to be really hard for them to implement that if they ever try. So for now, I don't know, maybe I'll just make everything one component. Components are kind of a pain. Being able to move them around is kind of cool, but ultimately I don't really need them to be able to do that in this design. So yeah, let's do what I was just about to do. We can turn off our plate body, and then I'm going to do an extrude, and I'm only going to select the holes. Okay, and we'll just extrude it up 1 millimeter. Actually, you know what? I'm going to do something else. I'm going to make a sketch, and I'm going to project I already know what I could do. quickest way to do this, I'll just turn the body back on and look at the bottom, right click on the surface itself. No, not edit sketch. Okay, I'll create a sketch on this surface. And now it'll automatically project everything, all the edges of that, which is awesome. And oh, it doesn't. Okay, we're gonna have to project the centers of these holes. That's fine. This is going to be our test sketch, test extrusion sketch. So we added those. Turn the body off for a second. And go to our sketches. Oh. All right. I guess you do have to do it explicitly. So now we've got all this nice stuff we can work with. So I'm going to do an offset. Guess I don't really want an offset of the entire thing. Let's go to the offset. Oh, we'll do an offset of the circles. That are the holes. You can't select more than one. Okay, right. Then, fine. I'll just do a circle. And we're gonna make some circles. And the whole point of this is that I'm gonna make extrusions that are a little bit smaller than the holes. So when I print it on my printer, I can just drop the plate onto it and see if all the posts go into the holes. And our final design, we're not going to have physical posts because we don't need any, because the standoffs in this case design already achieved that. Most 60% boards, at least the kind of mid-range and cheaper ones, I think all these equal, have standoffs that come from the bottom of the case and go up and screw into some part of the plate. But some people think that makes the typing experience too hard or inconsistent. I don't really notice that much of a difference. Also, if you're using a brass plate, it's so hard that it doesn't really matter that much. Our music paused. So we're gonna save this. Hold on a second. Cool. Okay. We're going to say this is hole, plate hole ID minus 0.2 millimeters. You can do math inside dimensions, which is pretty fun. I want to give ourselves a little bit more clearance. .9. Okay, let's try doing an offset around that. I'm going to 0.4 as well. maybe 3.3. And then we'll do another offset around that. Oh, Fusion doesn't like you doing an offset of an offset. Okay, so fine, we'll sketch the original one. And negative 0.5. Maybe 6. Let's make it 0.4 wide because it's 0.4 wide nozzle. So now we have this nice outer outline we can print. All right, so that sketch is done, and we'll just call this, oopsies, rename, test sketch. So now we do an extrude. Let's see, we're at the bottom. So we're gonna do an extrude of this circle and this one and this one and this one and this one and that one and the outline, and we'll just do it up, I don't know, 1 millimeter. There we go. Boom. So now we can 3D print just this stuff, just the outline and these posts. And they don't even need to be 1 millimeter tall. So we can just edit that. I mean, well, let's just make it the same as plate thickness. Ah, it's a little taller. That's okay, that'll give us a pretty good idea. Alright, save it, and then now we just go up to here and do save as STL. Hit OK, and then we'll put it in our mechanical keyboards folder, and KBD67 case, 11, test 1. Okay, and then I'm gonna open up Cura. I'm almost done. Man, this program takes a while to open. Okay. All right. Not ASUN PETG. Let's use, what I've got in there right now is this Pearl Rainbow stuff. I think it actually can be printed lower, like 215. That's fine. Okay, we're gonna open quick access this guy, and we're gonna need to rotate it 45 degrees would be the best bet. At the front of the printer. Okay. That should fit pretty good. So we're not going to have a lot of room to work with for the case. This is a 300 by 300 millimeter print surface. So the case can only, the corners can only extend out maximum to like around here. You don't want to get close to the edge because then you'll cause the stepper motors to like, cause something to slam into one of the end stops. So yeah, let's slice that. Oh, you know what? Do I have gap fill everywhere? Okay. Sure, let's preview it. It's gonna take 11 minutes, even with the skirt. You know what? We don't really need that. It does a wipe at the beginning. So there we can look at it. Is that as far zoomed in as I can go? That's weird. The posts are like two separate things. Is that like a zoom tool? Let's go back to Fusion and make sure we didn't do something weird. Nope. Alright, well that's fine. It's weird, you'd think it would do some more gap fill. Okay, whatever, saved a file. Quick access. Nope. That and Pearl Rainbow PLA. Okay, turn this off, and I'm just gonna go to my Octoprint. And can you see that? It's kind of off center. Anyway, I'm just gonna go to mechanical keyboards and make a new folder for KBD67 case. Go in here. What? No, go in here. Okay, upload. Quick access. KBD67 case PRPLA. Yeah, and then we'll click it. And let me turn Octolapse off, because we don't need to take pictures of that. And then we click on this one. Oh, we gotta connect. Okay, click on that and print it. And so the target temperatures go up, and yeah, soon it'll be 3D printing. Okay. Yeah, and I think that's going to do it for tonight. So yeah, that was the process of measuring a keyboard PCB and plate to be able to design a case for it. I'm going to do some iterating of printing and adjusting these measurements until the plate fits perfectly and everything is in the right place. I'm also going to probably model the PCB and have print out a little thing that shows where the USB hole should be and where the reset button should be, just like I did with these holes in the outline. And that way I can get everything in the right spot. Then I'll move on to actually designing a case in this file. And yeah, that's pretty much it. So, thanks everybody, and I hope you all have a